Hi, welcome back to my YouTube channel, Theoretical Physics with Mark Weitzman. I want to finish part 3 of lesson 9 on the path integral in interacting field theory. And before I resume the lesson, I just want to start. I want to correct an error that I made earlier, more like a typo. And hopefully it will have been fairly obvious. I wrote this for the interaction term as I wrote I z g the integral d4x for the vertex, and I left out the factor of g. So I left that out, and this is the correct vertex. Zg is a factor that will probably be of order g squared, so a 1 plus order of g squared. Usually this is 1 plus order of g squared. So if you're working to like order g, you just use 1 for zg, but you need the g in there. Okay, so now let's moving on. So we have our path integral z1g. This includes the interaction term This includes our interaction term, but no counter terms yet. Now, if we try and see how this works with whether we meet the conditions that we want to impose, so let's calculate with what we have so far the vacuum expectation value of the field phi. And this is gotten the usual way. It's a 1, not an I. Evaluated it when the sources are 0. And then using our little formula for W, for Z in terms of W, this is equal to now, if you recall, W1J includes all connected diagrams excluding vacuum diagrams. But since we are evaluating at j equals 0, we want only diagrams with one source. So the idea is simple. If we have a diagram with if we have a connected diagram with two sources, when we apply the functional derivative, that brings us down to one source. But one source, when we set equal to 0, we'll set that whole diagram equal to 0. So we have to have only one source to start, and then when we take the functional derivative, there are no sources left, so when we set j equals 0, it doesn't affect it. So we need only evaluate the following diagram. Since we are working to order G. So, if we go back to our dictionary, we'll get a G from the vertex, and that will that's all we need. So let's do this. We have W1J at J equals 0. We have 1 over I del Jx of this diagram. Call this X, Y. X and Y are space-time points. And then after we evaluate it, we'll set J equals 0, but there won't be a J anymore, so that won't really matter. This diagram has a symmetry factor of S equal 2. So this is equal to 1/2. That reflects the symmetry factor. And then we use our dictionary. We have IG, the integral of when we take the derivative of the source, we're just going to be left with 1, because we have a we have a del Jx of the source that gives us a delta function at that point. Then we're integrating over that point, so the integral of a delta function is just 1. So the dark source evaluates to 1 after we take the derivative. And then we have the integral of d4y. And we have to have I, the propagator from x to y. And then we have, going around the loop, 1 over I. This looks a little funny, del y minus y. But if you think of it, that's what we do. We go from point y around the loop to y. I'm not going to put an arrow on that loop because these are not charged particles, so there's no direction. You can go any way you want around the loop. Antiparticles and particles are the same in this scalar theory. So anyway, this is the dictionary. You have to practice these things, converting the diagram to a mathematical expression. And we neglect the ZG because that's about 1 plus order G squared, so we just use the 1 for the ZG. Okay. Now, this expression over here, besides looking very fishy because of this del y minus y or del 0, kind of tells us we're going to have a divergence or we have a problem. But the most important problem is this is is non-zero. So now to fix this, we use a counter term. To fix this, we introduce a counter term, y phi, and add the following to our dictionary. So now we basically have a line. Counter terms are usually denoted with a cross symbol, or a large X, or a small x. And the mathematical expression here is I times y times the integral of d4y. So this is the space-time point y. Just a single line. Okay, so this is the name of this is our y counter term. And so taking into account this diagram, we get the following to order G. We're going to have to take into account, I'm sorry, 1 over I. You know what, let me start this on the new page. Sorry. 1 over I del jx this is at the point x, and then at the point y we're going to have our new counter term diagram. The symmetry factor for this factor is just 1, yeah, and evaluated at j equals 0. So altogether, our new vacuum expectation value is equal to, so we're going to add, once again, when we take the derivative of the source x, it just sets it equal to a delta function, and then when we integrate over x, it's just 1. So that disappears, and we have iy plus what we had previously, 1/2 ig 1 over I del 0. So I just factored that out. And then once again, we have the integral. This is point x, this is point y, where the counter term is at. The integral of, and the loop, the integral of d4y 1 over x del x minus y. So you can see, once we apply the functional derivative to the source at x, it just wipes it away. And then we're left with two diagrams, one of which is the counter term diagram, which is just iy, the integral of d4y, I don't know why I wrote x there. This is 1 over I del x minus y. And so we go from the point x to point y, we have a propagator. And that takes the counter term, that's all we have. And then when we have the other diagram with the loop, I probably should show it just adding it as I did earlier. So we're going to add these two diagrams. This gives us our total expression. Now we want this to be equal to 0. And to accomplish that, we simply set this requires that y equal to 1/2 ig del 0. Simply put up y equal 1/2 ig del 0. You could see that in one term we have an I, in the other term we have a minus a 1 over I, so where that converts to a minus I, so the total is 0. Now, so that's like to order G what the counter term has to be. And this must be real. Since y appears in the Hamiltonian as the coefficient of a Hermitian operator. Remember, phi is Hermitian because we're working in scalar theory, a neutral scalar field theory. Now, del 0, by our usual definition of the Feynman propagator, all it does is take away the exponential factor. d4k 2 pi to the 4th 1 over k squared plus m squared minus I epsilon. And it's not obvious that del 0 is pure imaginary, and it diverges. You can see the divergence because a d4k is essentially a k cubed dk, and then we have k squared in the denominator. So we're integrating something which is like that, or we're integrating something which is like k dk, and so this ends up being like a quadratic divergence. Now in field theory we're going to encounter divergences all the time, so we don't panic. But and we call this type of divergence a ultraviolet divergence, because it diverges as k goes to infinity. So remember, k is a momentum, so that's sort of like a short distance divergence. Distance goes to 0, momentum energy goes to infinity. We'll also encounter later in the course infrared divergences, which go as k goes to 0, and those are a different kind of divergence. Those are usually what we consider to be an experimental divergence, but we'll talk about that later. So just to give you an outline, we're not going to actually do it for a couple of lessons, but we proceed by introducing a cutoff lambda to ensure convergence. And we have to do this in what we consider to be, this is the key thing in quantum field theory, and this is what Feynman, Schwinger, and Tomega and Dyson did early on, is that we need to introduce these cutoffs or renormalizations in a Lorentz invariant, gauge invariant way. Now, this theory, we don't have to worry about gauge invariance for scalar field theory, but we do have to worry about Lorentz invariance. So we can't just put like a lambda, this won't work, you know. We can't just say, well, we'll integrate up to lambda. Because in one reference frame, lambda could be very big, and in another reference frame, we could boost so that lambda is small. So that doesn't work. And what we need to really do is to do something like the following. We modify our propagator so we have something like the integral of d4k over 2 pi to the 4th e to the I k x minus y k squared minus m squared minus, k squared plus m squared minus I epsilon. We will do something like lambda squared divided by k squared plus lambda squared minus I epsilon. So this wouldn't be enough because we have 3 powers of k in the numerator here, and we would have 4 powers of k in the denominator. We would still have a logarithmic divergence, but if we square this, we'll be okay. So now we'll have something that goes like integral k cubed, say dk, k cubed divided by k squared, and then a 1 over k to the 4th. So we're going to have, this is about integrating like 1 over k cubed, which will clearly converge. And then when k is very small, this thing, just when k is 0, this just becomes 1. So we don't introduce, we're good there. So this is sort of what we do. And there are other ways there are many ways. This is sort of like the Pauli method of doing, introducing a convergence factor. But there are ways or other ways, more modern, like dimensional regularization, which we'll talk about later. So in section 14, we will find, when we actually calculate this, that for lambda much, much greater than the mass in the theory, del 0 is equal to I lambda squared over 16 pi squared. So in fact, y is real, which is very good for us. But when we take the limit, as we want to do with all these artificial parameters that we introduce, when we take the limit as lambda goes to infinity, y will go to infinity. And that's not that good, but remember, y is just a superficial parameter in the theory designed to cancel all terms. All terms as needed to make the vacuum expectation value equal to 1. So this may not be that serious. And in fact, since y will be shown to be order g, we'll find that measurable quantities such as cross sections all the formally infinite terms will cancel in a well-defined way. Obviously, Zernecke and I are just hand-waving here, but this will be shown later on, so we haven't shown it yet. This is the essence, the renormalization program covered in sections 14 to 20. Okay, good. So what we do is, when we add the higher order terms, when we calculate to higher order, we adjust this non-physical parameter to maintain equal to 0. So the value of y is determined order by order in powers of g. Now, so moving on, so this vacuum expectation value equaling 0 implies that the sum of all connected diagrams with a single source is 0. So you could think of having like a single source here, and then we can have like this diagram which we calculated, and then we can have another diagram with a single source that goes like so like this, but we can add like another bubble here if we want, and so on. When we add all these up, the sum of all these diagrams is equal to 0. Now, if you remember how we evaluate this, we always take a functional derivative on this source, which basically just turns it into a delta function, which wipes it out, which basically means 0. So this really means that this is equal. We can sort of take the source away. That plus that plus that, plus dot dot dot. This is also equal to 0. So if we have any diagram, any subdiagram, like let's take a subdiagram like this. And we add that onto all these other diagrams. We combine that with like this, and then we do, I'm sorry. Now we combine it with, let's say this and this, and you can, what we're doing is we're adding, this is the sub diagram. Oops, I drew that in the wrong place. So it's the same thing again. We're going to have some kind of blob. That's the oops. No, I don't want it erased. Anyway. This is the subdiagram. And we can disconnect it from our series, all these other diagrams with the single source. So this also has to be equal to 0. Because again, the way we're going to calculate it is we're going to, whatever this mathematical expression represents this subdiagram, we can sort of cut it off or factor it out. And we get back to here again, which equals 0. So this results in a pretty big simplification. So any diagram that we can cut off, where we can, with a single line, cut it off to have no sources in them. So diagrams, these are called tadpole diagrams. Can be ignored. This is a tadpole, because we can make a cut here, a single cut here, and now we have a diagram, with no source. So anytime we can split a diagram into two parts with a single cut that has no sources, we know that the sum of all these is equal to 0. Again, going back to here. So that simplifies a lot. As a matter of fact, now we only have to consider diagrams, as we'll see, with basically two sources, because if there was only one source, we could always cut it into two parts, one of which has no sources, and then those all add up to 0. So we don't have to take that into account. So finally, the last thing in this chapter, we have to take account of the remaining counter terms that we haven't discussed yet, and I'll write them down in a second. We define A, this is just a definition, z phi minus 1. Remember, we expect the z's to be of value 1 plus order g squared, so when we subtract 1, we expect the a's and the b to be of order g squared. And the actual counter terms in the Lagrangian or the Hamiltonian were 1 minus 1/2 a partial mu phi minus 1/2 b m squared phi squared. So we have our new complete interacting path integral will be equal to exp, and I'll just write it down, minus I over 2 integral d4x 1 over I del jx minus a partial x squared plus b m squared 1 over I del jx operating on z1j. Now, z1j is not the same thing we had before. This now includes the y counter term. And how do we get this expression? Well, first of all, we integrated this by parts. So this just becomes phi partial squared phi, becomes a minus. So that's just integrated by parts. And then if you remember, we always multiply by e to the I times the part in the Lagrangian. So when we have minus I times minus a, we get plus a. That's what we get here, because when we integrate by parts, we have minus 1/2. So we have the 1/2. That's the I. And then we're going to have, so the a term is positive, and the b term remains negative. So that's correct. And these are we substitute these for phis, because we always go like L1 1 over I del jx. So when we do the integration by parts, or when we have the b term, we have a phi term here and a phi term here, and we replace that by 1 over I del jx. So that is the mathematical expression of our thing. And now let's just add to our dictionary. What it is when we have a propagator, when we have two lines meeting, so consider this like y and z. Now we have this counter term. Now this is not the y counter term. The y counter term only has one line. This counter term has two lines. It has two fields. So this is the mathematical expression here is minus I, the integral of d4x minus a partial of x squared plus bm squared. Okay. But the important thing is that this acts only once. So for instance, if I have a point y and z, the whole expression here is going to be 1 over I propagator del x minus y. And then I have minus I, we're multiplying, minus I, the integral of d4x minus a, the partial of x squared, plus bm squared. And this whole thing will be followed by 1 over I del z minus x. So this thing over here, it can either act on the propagator to the right, or it can act on the propagator to the left, but not both. So pick one, and you can act to the right or you can act to the left. Remember, this integration by parts for a partial squared will not introduce a minus sign when we do it twice. So that finishes this chapter, and in the next chapter we'll convert these diagrams in dictionary. We'll convert them to scattering amplitudes, and then in the following chapter we'll start calculating cross sections. So thank you very much for watching. I'll see you next time.